motion, whatever cases we have seen, all the laws were derived, application of the laws when the mass was taken as constant, isn't it? F is equal to m into a. Condition was when mass was constant, isn't it? Newton's second law. But when mass varies and velocity remains constant, then also force will have to be applied. So that can be seen, just I will explain. See, we know that according to Newton's second law, that force applied, external force applied, it is directly proportional to rate of change of momentum that we have already studied. That is, F is directly proportional to dp upon dt, where p is, of course, it is the momentum, that is linear momentum. Therefore, F is equal to, and this is k dp upon dt, and we have put the value of k as 1 because force was defined like that, 1 Newton force. This I have already explained, right? Therefore, F is equal to dp upon dt, taking k is equal to 1. Now, why did I take k is equal to 1? Because when F is equal to k and a, then force F, that is 1 Newton, is defined as the applied force on 1 kg mass, which creates the acceleration of 1 meter per second square, that is called 1 Newton force. That is 1 is equal to k into 1 into 1, that is why k is equal to 1. That is the definition I have already given in the previous videos if you look at it. So F is equal to dp upon dt. And what is P? Therefore F is equal to, if we differentiate, that is m into v. Here mass into velocity, that is the linear momentum. If we differentiate this with respect to time, we will get, therefore F is equal to v dm upon dt plus m dv upon dt. That is product of two variables. M is also variable, v is also variable. Where previously what did I do? M I had taken as constant, that is why m was taken out, and in that case dv upon dt was the acceleration a. Here I have taken both are variable, right? M, v, both are variable. But if only mass is varying and velocity is kept constant, what will happen? But if v is constant, then dv upon dt will be equal to 0, because v is constant, this part will be 0. Therefore suppose it is 1, therefore from 1 F is equal to v dm upon dt. This relation is very important because dv upon dt will become 0. So this part will become 0. We will get only this part. So this is the variable mass system where velocity is constant and the mass of the system is varying. So this will be the amount of force acting on the system, right? So this is very important relation, and the biggest example is the propulsion of rocket. That can be understood like this. Rocket propulsion. See, I have made this system. This is the rocket at particular instant t. I have assumed its velocity is v. Right? During the span of delta t, suppose delta m mass of fuel burnt and the gas produced, and it is removed from the system. So system, what is system over here? system is equal to the rocket plus unburnt fuel. So this is the system. At any moment, when its velocity is v, it has got some amount of fuel also. At time t, the mass of the system is equal to m. After delta t time, delta m mass has come out after burning, isn't it? And it has gained the velocity v plus delta v. So after that time delta t, what is the mass of the system? Therefore, after time t, time delta t, the mass of the system is equal to m minus delta m, because this much mass has come out from the system, isn't it? And the velocity at that moment is v plus delta v. Therefore, the momentum of the rocket at time t plus delta t is equal to m minus delta m into v plus delta v. Am I right? See, one more thing, that is that I have taken the velocities. This is one part. We'll proceed further. Suppose with respect to rocket, the gas comes out towards downward direction with velocity vr, and with respect to earth, observer is standing on the earth and he is observing. Two things are separately we will look at: velocity of a rocket and velocity of gas. Gas is coming down. With respect to rocket, it is coming down. But with respect to observer on the earth, gas is going up. Two things are there. With respect to rocket, it is coming down, because when the observer is there in the rocket, he will say that gas is going downward. But since rocket is also moving up, so along with the rocket, the person who is standing on the earth, he will say that gas is also going up, isn't it? That is why velocity of gas with respect to earth is v dash, and velocity of rocket with respect to earth is v. That I have already taken. It is going up. So we can write velocity of gas with respect to rocket is equal to velocity of gas with respect to earth minus velocity of rocket with respect to earth. This is the basic phenomenon which I have told you previously also. Now, what is velocity of gas with respect to rocket? It is downward. So I will take downward direction as negative and upward direction as positive. Suppose we are taking like this. So VGR is VR. So we will write VR. Since it is downward, we will take as negative. Right? Downward direction is taken as negative. Either way we can select. We can take the downward direction positive also and upward direction negative. As per our selection, things will be written over here. VGE. GE is upward. So we will write V dash minus VR. RE, it is also upward. So that we will write V. Therefore, V dash is equal to V minus VR. This is important. What is V dash? V dash is the velocity of gas with respect to earth. So whole observation is being made from the earth. This is the velocity of the rocket at the time t plus delta t observed from the earth, isn't it? So now if the system as a whole, if you look at, then what will be the momentum of the system at the time t plus delta t? This is the momentum of the rocket, and momentum of gas will also be added in this. Therefore, the momentum of the system at t plus delta t is equal to momentum of the rocket plus momentum of ejecting gas, right? So momentum of the rocket is this much, that is m minus delta m v plus delta v plus, this is the velocity with respect to ground. Velocity of what? Velocity of gas, right? And mass ejected is delta m. So I will write delta m here, because v dash is the velocity of the ejecting gas with respect to ground. So delta m into v dash is the momentum of the gas ejecting, and that is the momentum of the rocket. So combined momentum will be the total momentum of the system. This is the total momentum of the system. Now, initial momentum, if you look at it, initially mass of the system was m. So initial momentum is m into velocity v, right? Because after time delta t, velocity was changed. Therefore, that is equal to, we can write m minus delta m v plus delta v plus delta m v minus vr, v minus vr, right? So we can simplify this, that is equal to multiplied mv minus delta m v plus m delta v minus delta m delta v plus delta mv minus delta m vr. So delta mv here, delta mv here will go, and this delta m into delta v, it is very small quantity, and product of small quantities is further small. Are you getting my point? It is very small quantity, isn't it? Delta m, delta v is also very small. So product of two small quantities further smaller. That is 0.1 into 0.1. How much it is? 0.01. It is smaller than 0.1. So it is very small quantity, and we can neglect this quantity. Therefore, so we can write mv plus m delta v minus delta m vr, right? Neglecting delta m delta v, this quantity. So we have got final momentum is this. Therefore, change in momentum. Therefore, change in momentum. Change in momentum is equal to mv minus m delta v minus, it is plus, delta m vr, isn't it? Minus mv. Therefore, this is mv and mv will go. We will get, that is m delta v minus delta m vr. Here one thing we know, that impulse is equal to F external into delta t. That we know, external force applied for a short time, then product of this force and the duration is called the impulse. And impulse is equal to change in momentum, right? It means this change in momentum is caused by the impulse on the system, isn't it? So here, what is external force? In this case, downward force mg is acting. Mg initial this was the situation at time t. Only external force acting was downward, and downward direction I have chosen as negative. Therefore, that is F external is equal to minus mg initially. This force was applied for duration of delta t. In delta t, whatever is the change in momentum, that will be equal to impulse. Therefore, impulse is equal to minus mg delta t, and this impulse is equal to change in momentum, that we know, right? Therefore we can say minus mg delta t, that is equal to change in momentum. Change in momentum of the system, since impulse is equal to change in momentum of the system, right? So therefore minus mg delta t, that is equal to change in momentum is this. We have got m delta v minus delta m vr. Therefore we can write m delta v is equal to, this is equal to, I will transfer this, so delta m vr minus mg delta t. Divide whole equation by delta t, we will get m delta v upon delta t, that is equal to vr delta m upon delta t minus mg. For this duration delta t, this equation we got finally. If this duration is very small, infinitesimally small, limiting to 0, right? If this delta t is limiting to 0, we can write therefore m limit delta t tends to 0, delta v upon delta t, right, is equal to vr limit delta t tends to 0, delta m upon delta t minus mg. This is the constant quantity for the beginning. This we know, therefore m into dv upon dt is equal to vr dm upon dt minus mg. So it is very important relation. So what does this imply? Mass into dv upon dt. Mass is the initial at the time t. This is the system of the system. Now this is the acceleration, right? With this acceleration, the whole system will be moving. This is the rate of change of mass of the system. dm by dt, mass of the system, it is decreasing, right? Vr is the velocity of the ejecting gas with respect to rocket, and this is the initial weight of the system. This is very important. What is the significance of this relation? This part is this mass is the initial at the time t, what is the mass of the system, and this is the acceleration of the system. So this is the net force on the system. So net force means what? This is, suppose this is the system I have taken, mg is acting downward, some force, that is thrust, is acting, I will say thrust by the gas is coming downward, thrust is acting upward. So upward thrust and mg downward. So upward thrust, suppose if I say F, right, upward thrust is F. So net force will be F minus mg, right? So net upward force is equal to F minus mg, and this net upward force is creating, this is equal to this. So you see, if you look at compare these two, then upward thrust F is equal to this. Therefore, upward thrust, that is 1, and if it is 2, then from 1 and 2, upward thrust F is equal to what? This VR dm by dt. This F is equal to this. So we have derived this equation where m is the total mass of the system, rocket plus unburned fuel. This is the acceleration of the system. This is the amount of fuel getting burnt in unit time, rate of burning of fuel. Now suppose in the beginning when the system was at rest, right, means mass of rocket and the mass of fuel, total mass, when there is no acceleration, nothing, in the t is equal to 0, right, it is at rest, and the mass of the system is mg. Let the mass of the system means, whenever I talk about system, means this is rocket plus unburned fuel, right? Mass of system at t is equal to 0, that is at rest, is equal to mg. And the rate of consumption of fuel, it is dm by dt. So in time t, what amount will be consumed, right? So therefore, the amount consumed, amount of fuel, I will say, fuel consumed during time t is equal to dm upon dt, because this is a rate, in unit time dm mass is getting consumed, into t, right? So the amount, total mass after time t, mass of the system, therefore the mass of the system after time t is equal to m0 minus dm upon dt into t. This will be the mass of the system. System is rocket plus unburned fuel. So after time t, how much will be the mass of the total system is this. And what is m? M is the mass of the system where rocket and unburned fuel is there. So if, suppose this is the equation 1, so equation 1 can be written like this. Equation 1 can be written as dv upon dt is equal to vr dm upon dt divided by m minus g, right? So this is the acceleration of the system, right, after time t. Suppose I say after time t, what will be the acceleration? So at that moment, what is the mass of the system we have to take? Therefore, here m is equal to this much, m0 minus dm upon dt into t. Therefore, dv upon dt after time t is equal to vr dm upon dt divided by, this is m0 minus dm upon dt into t, right, minus g. This is also very important relation. Many numerical problems will be solved. As rocket goes up higher and higher, the value of g will be lesser and lesser. At higher altitude, g is getting reduced. That is, gravitational pull by the earth will be reduced. And simultaneously, this denominator will be also reduced. Why? Because this quantity will increase. More and more fuel will burn, so denominator will also be less. This will also be less. If you look at this, as this is getting reduced, whole quantity will increase because subtraction is less. If denominator is reduced, whole quantity will increase. Means as rocket goes up, its acceleration will go on increasing. At very high altitude, we can consider G as 0. We can say at very high altitude, G is equal to 0. Therefore, dV upon dt we can write VR upon m0 minus dm by dt into t into dm by dt at very high altitude. This will be the acceleration of the rocket. Rocket means I am talking about the system. Acceleration of the system will be this much. So these three formulae, first this one, right? Second this one, and third this one. These formulae will be applied to solve the numerical problems. So I will take a few numerical problems, the concept will be more clear to you, right? So see the question. A rocket burns 50 grams of fuel per second, ejecting it as a gas with the velocity of 5 into 10 to the power 5 centimeters per second. What force is exerted by the gas on the rocket? So I will write what is given. So that is 50 grams fuel per second, means rate is given. So here dm upon dt is given, that is 50 grams per second, right? And this is the velocity, that is Vr is given, velocity with respect to rocket it is, that is 5 into 10 to the power 5 centimeters per second. Now the information given is a CGS system, grams per second, centimeter per second. So whatever value we will get, that will be in terms of dyne, that is unit of the force. And when we know that thrust F is equal to Vr dm upon dt. In the beginning only, first formula I had derived, that is Vr into dm by dt is the thrust by the gas in upward direction. So you put the values and you will get the value of F, that is Vr is 5 into 10 to the power 5, that is 5 into 10 to the power 5 into dm by dt is 50, right? So how much it is? That is 250 into 10 to the power 5 dyne. And one thing we know, that 1 Newton is equal to 10 to the power 5 dyne. Therefore, that is 250 Newton. This is the answer. Why it is? Since 1 Newton is equal to 10 to the power 5 dyne. Do you know this relation? I will show how is it. 1 Newton is equal to 1 kg into 1 meters per second square. That is equal to 1 Newton, isn't it? 1 kg means it is 10 to the power 3 grams into 1 meter is 10 to the power 2 centimeters per second square. That is equal to 10 to the power 5 grams centimeter per second square. And this quantity is dyne, therefore 10 to the power 5 dyne. Therefore 1 Newton is equal to 10 to the power 5 dyne. This only I have mentioned over here. So this way answer of this question is 250 Newton. See this question. A rocket of initial mass 6000 kg ejects mass at a constant rate of 16 kg per second with constant relative speed of 11 kilometers per second. What is the acceleration of the rocket a minute after the blast? G is given. So what are the data given that we will write first? So what is given? Initial mass, if you remember, previously just you have seen a few minutes earlier, that initial mass I have taken m0, right? Where at t is equal to 0, there is no ejection of mass. At that time, what is the mass? That is m0. That is 6000 kg, right? Then rate is given, that dm upon dt is given, that is 16 kgs per second. What else is given? Relative speed is given, that is Vr is given, that is 11 kilometers per second. So in SI system we will convert this to 11 into 10 to the power 3 meters per second. All the data is in SI system now. One more thing, because what is required after a minute, what will be the acceleration? So at that time I will have to find the mass. After a minute, what will be the mass of the system? System is rocket and fuel. So unburnt fuel, whatever is left, right, that will have to be considered. So burnt fuel will have to be subtracted from this mass, right? So we will say the amount of fuel burnt in 1 minute. 1 minute is equal to, this is burning in unit time, that is dm upon dt into 1 minute means 60 seconds, because it is 16 kg per second it is. So this minute will have to be converted into second. So this is the amount burnt in 1 second and multiplied by the total amount of the fuel burnt. That is equal to this much, that is 16 into 60 kgs. Right? Therefore, m is equal to what? m0 minus this quantity, isn't it? That is, we can write, this is, formula is m is equal to dm upon dt into t, and this quantity dm upon dt into t is this. Therefore, this is 6000 minus 16 into 60 kg. This is m, because this is the amount, which is, this is the mass of the system after 1 minute. So we will use the formula, that is m dv upon dt is equal to Vr dm upon dt, right? Or we can write, simplify this, therefore dv upon dt is equal to Vr upon m into dm upon dt minus g. So put the values, that is Vr is, we can write 11,000 upon m is this, that is 6,000 minus 16 into 60, right, into dm by dt, again it is 16 minus 10, g is 10. Solve it and you will get the answer. This is 11,000 upon 6,000 minus, that is 960 into 16 minus 10. Then further simplification, this is equal to 11,000 upon, that is 5040 into 16 minus 10. This 0 will go, that is equal to 2200 upon 63 minus 10, that is, it is 6 34.9 minus 10, that is 20. Therefore, dV upon dt, that is equal to 24.9 meters per second square, and this is the answer. Now concept is clear. All the best. Take care of you.